Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar lecture theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar. Friends, welcome to the 7th lecture on the Marine Renewable Energy System course offered at IIT Gandhinagar in the Swayam Prabha portal. In lecture number 7, we will discuss about more details on the numerical model of wave energy converter in frequency domain approach, which can be actually a continuation of the previous lecture. However, as I requested you, you should follow all the lectures of this course to have a comprehensive and overall understanding of the entire course. So therefore, in this lecture, friends, we will slightly borrow certain information from the previous lecture and then from that point we take off to explain the numerical formulation of the problem of primitive design of wave energy converters. So friends, we already said that frequency domain approach is useful to conduct primary analysis of the newly proposed wave energy converter. So, we already said the total force at which the equation of motion is represented comprises of hydrodynamic forces. The hydrodynamic forces can be further classified as excitation forces arising from the waves and the radiation force which is produced from the motion of the system. Okay. The excitation force is further classified into diffraction force, which is arising due to scattering of waves, the scattering happens in the presence of wave energy converter. Okay. And then the Frau Trailoff force which is actually the pressure acting on the virtual wave energy converter in the absence of waves. Okay. The diffraction theory presumes that wave energy converter is very large in size compared to incidental wavelength. Therefore, the presence of the structure itself is felt and therefore, the wave gets diffracted. So, that is an assumption made in this analysis. The radiation forces are the WEC induced forces. They are WEC generated forces because of oscillations of the WEC in combat. Generally, these waves are generated outwards from the WEC. Therefore, the net effect of radiated waves and instant waves. Instant waves approach the wave energy converter, radiated waves come from the wave energy converter. Therefore, the net effect of instant waves and radiated waves is complex. This produces a complex wave WEC interaction. Okay. It can be positively or negatively affecting the performance of WEC. So, now this complex formation can be advantage or disadvantage to the proposed WEC. We do not know. This is where the efficiency matters. Okay? So, this is where the geometric dimension, the size, place, position, damping and the buoyancy characteristics of the WEC need to be redesigned, because sometimes this net effect can also be negative for the chosen configuration. It may radiate too much, it may not radiate at all, let us say, okay, the extreme cases. It can affect the WEC design. Therefore, friends, we repeatedly say that the frequency domain approach used in WEC design is only primitive. It's only first order, preliminary. Okay. Now, the radiation force comprises of added mass, and radiation damping. The added mass term is an additional inertia force which is generated by the accelerated fluid around the WEC. How this has happened? This has happened due to oscillation of the WEC in water. Okay. Now, generally this will be in phase with the WEC motion. That is a very important point which we need to remember. So, this is or this will have no contribution in negating the performance of wave energy converter for a given input force. Okay. Let us look at the radiation force. The radiation damping is dissipation of energy and this generally happens as an outgoing waves which will move away from the wave energy converter. Generally this will be out of phase of the wave energy converter motion and it will be in phase with WEC velocity. Therefore, the radiation damping is proportional to the WEC velocity with the proportionality constant as radiation damping coefficient. So, we use a proportionality constant which is called radiation damping coefficient. The next component is the hydrostatic force or the restoring force. The restoring force is actually the difference in equilibrium between the gravitational force and the buoyancy force. This is proportional to the wetted surface area at mean sea level. So, friends, this part and parcel of explaining these force components will help you to understand the contributors which will add to the performance of the WEC or negate the performance of the WEC. So, one should understand which segment contributes to the positive side and which one the negative side. So, having said this, let us put this in equation form. We now say F total, which is a function of frequency. I am doing frequency domain analysis. So, which is Fk, the Freud-Kraloff force, sum of Fd, where Fd represents the diffraction force, all in complex domain, okay, plus Fh, where H represents complex hydrostatic force, plus F hat PTO represents the complex PTO force, plus F hat M, which represents the complex mooring force, because equation number 3. So, I can say F hat Fk represents complex Freud-Kraloff force. F hat D represents complex diffraction force. F hat H represents complex hydrostatic force. F hat PTO represents complex PTO force. F hat M represents complex mooring force. Okay. Now, the force estimated by the above equation is actually obtained by integrating the corresponding pressure difference over the WEC surface. Okay. So, this can be obtained by integrating the corresponding pressure over the WEC surface. So, I must use something called surface integral. Okay. So, it should be over the surface integral, and I should use this. Of course, the pressure can be obtained from first order Bernoulli equation. Which can be given as P equals minus rho dou phi by dou t. Let us talk about the radiation potential. The radiation potential is assumed to be active in all degrees of freedom. In man, to be very clear, in all free degrees of freedom. There can be certain degrees of freedom which are restrained to move, for example, heat, right. So, all free degrees of freedom, you have radiation. Okay. So, therefore, I can now rewrite this equation. Equation 3 can be rewritten as F hat total frequency function is I omega rho surface integral phi hat 1 or phi hat I plus phi hat S n ds, whereas phi hat I represents instant wave potential. I write it here. Phi hat I represents incident wave potential and phi hat S represents scattered wave potential plus I omega rho integral surface P dash R NDS surface integral, where phi dash R represents radiated wave potential minus, there are some negative effects to this force, rho g s x omega minus I omega C PTO, because PTO will cause damping to the system, which depends on the response of the device, minus PTO will also have a stiffness because of its mass proportional damping, and will also have the force coming from the mooring lines, which is also a function of the complex response function of the device. So, we call this equation number 4. So, let us look at this equation. The first term is a complex exciting force. Okay? The first term is a complex exciting force. So, I can now say I can write it here. Now, we can say the complex exciting force, which is a function of frequency, can be a sum of complex exciting the Freud-Krylov force plus complex D, the diffraction force. The second term in this equation is a complex radiation force. Okay? The second term is complex radiation force. If I write this force by saying J represents the mode and N represents the number of free modes. All modes may not be free, right? So, we can say there are 5 degrees of freedom, 5 modes of vibration, all may not be free. Therefore, amongst the jth mode given, a few of them will be free modes, right. So, now I can express the radiation force as minus omega square rho surface integral. I integrate this from j equals 1 to n only. Okay. So, xj complex variable of Pj surface integral ds, where I can call this equation as 6. Pr, the radiation complex variable, is actually I omega times of j equals 1 to n of x hat j of omega phi j. This particular term will be split into the energy dissipation term and added mass. So, this particular term will be split into energy dissipation term and added mass term. Therefore, the product of complex radiation force under the complex velocity and proportionality if I represent this by the complex radiation force, which is actually a function of complex velocity and proportionality term, can be expressed as f hat r minus I omega x hat omega z r, equation number 8. I can now compare the expanded form of this to any one degree of freedom. So, if we expand this to any one degree of freedom in radiation, then Zr can be said as minus I omega rho surface integral phi n s ds. Is it okay? And this is called radiation impedance function. Okay. Now friends, in electric terminology, impedance function is a complex function. Now in this complex function, the real part represents resistance, and the imaginary part represents reactance. That is in general in electrical technology. Now in WEC terminology, in wave energy device terminology, Zr is given as minus I omega rho surface integral phi n ds. This can be equated to r omega plus I of I omega. Now the real part r refers to radiation damping coefficient. The imaginary part of I omega refers to added mass. Therefore, friends, the Zr hence Zr is referred as CRD omega plus I omega AM omega. Okay. So, this refers to the added mass part and this refers to the radiation damping coefficient. Therefore, Zr is actually expressed like this as well in the literature. Okay. Now, the real and imaginary parts of this equation are derived using Cramer's chronic function and Haskins relations. So, you can see this in detail. I am writing the reference. We are not touching that part here because it will be too much of mathematics at this moment. So, I can ask you to refer this more detailed derivations at these references. Newman 1962, Foley 2016. Please refer to this literature to know more about the detailed derivations of the real and imaginary parts of this specific ZR function. So, we have discussed about the first term, which is the energy input term, second term is the radiation damping term, the third term is the complex hydrostatic force. Which is actually given by rho Gs, equation number, I should say this equation number 10, okay, yeah, equation number 11. The fourth and fifth terms represents PTO damping, which is called CPTO, damping coefficient, and the spring terms, which will represent the stiffness of the PT. Okay. The last term in the equation represents the complex moving force, which is given by Km, which is actually proportional to the linear moving stiffness. If it is an axial cable, it can be simply AE by L. So, therefore, friends, after understanding them, the classical equation of motion can be written as in frequency domain as minus omega square m plus added mass coming from function of frequency as x hat omega, the complex function, minus I omega, the damping coming from the radiation damping, which is a function of c omega x hat omega, plus rho g s x hat omega, plus I omega comes from the damping of CPTO, which is x hat omega, plus the stiffness of PTO, which is again x hat omega function, plus the mooring force, which is coming from the mooring line of x hat omega, is now my exciting force. Equation number 10. So, this is 11. So, I should say this is 12. Equation number 12. So, friends, we have now refined the equation of motion by incorporating all our discussions of each and every term based on this. So, substituting this, I can now find the complex variable as below. So, now the complex amplitude of motion of the WEC, which is the desired quantity to design the WEC, is it not? It is the desired quantity. I am looking for this quantity only. So, I solve this equation, solve equation 11 or 12, 12, equation 12 to find this amplitude. So, I am not solving it here for you, but I am writing the equation directly. So, x at omega is given as F, the exciting force of omega, mod value minus omega square m plus am added mass omega plus mooring stiffness plus hydrostatic plus PTO stiffness, the mod value plus, it is not the mod value, actually this is one term, sorry, this is one term plus I omega of the radiation damping and the PTO damping. So, I call equation number 13, which will be the amplitude of the WEC which I want as an output from the design or from the analysis. Okay. So, if I know the displacement amplitude of the WEC, then I can always find out the output quantities as response amplitude operator of the WEC. Then this will lead to finding out the correct forces of PTO in terms of damping and radiation and the stiffness of PTO, which will redesign the PTO and again work on the better efficiency of the geometric form of the wave energy converter. Okay. So, friends, let us come to the summary of this lecture. In this lecture, we discussed about details of the forces in the equation of motion of wave energy converter in frequency domain approach. We understood the contribution of each term in the wave energy harvest. Some of them may be additive, some of them may be compromising or compensative, that is plus, this is minus, but they are required to find out the amplitude of motion of the WEC, based on which I will now design the PTO damping, PTO force, and then I will try to suit this to my modified design of wave energy converter. So, friends, the frequency domain approach is a primary analysis to estimate some important parameters of PTO, to estimate some important parameters of vibration of the WC, based on which we will able to find out the captured power of the converter for a given input power from the waves, which actually we call mechanical efficiency of the wave energy converter. Okay. So, friends, please follow up the remaining set of lectures in this course of Marine Renewable Energy System Design offered by Department of Maritime Engineering at IIT Gandhinagar. Please post your questions and queries to email to me in Swayam Prabha course outlet. Please look into all the references cited in this course for better and additional learning, in addition to the reference textbooks which has been recommended by the instructors for following this course well. Thank you very much. Namaste. Stay connected.